Okay, so a box of mass 0.2 kilograms is projected across a horizontal floor with an initial velocity of 2 meters per second. Okay, while it is moving, the box experiences a resisting force of 0.4 plus 0.6 V newtons, where V is the speed of the body of the box. Okay, so find the time taken for the box to come to rest. So if we sort of represent a box like this here and we draw some forces in, and to start with I'm going to have my direction of motion. Okay, so we'll have it go in this way, so we'll have our acceleration arrow pointed in that direction there. Now resistance to motion, it's got this resistive force. Okay, obviously we'll oppose it, it's going to go in the opposite direction that it's heading in, so it's all of that there, 0.4 plus 0.6 V. Okay, now there's no forward force, okay, there's no driving force pushing it forward, so in a sense it's just going to slow down. Okay, initially it's given a projection, okay, so it's given a bit of a push and it's given that speed of 2 meters per second right at the beginning, but following that initial projection there's no more forward force. So the only force we've got is the force that's slowing it down, this collective resistant force here. Okay, so to find the time body comes to rest, first thing we need to appreciate here is, because we've got motion, is we need to apply Newton's second law, okay, of motion, and I always put here in brackets in the direction of increasing motion. Okay, I always sort of state that because it helps me to appreciate then that when I work out the resultant force, I know what forces are positive, which forces are negative. Okay, so Newton's second law states that the resultant force is mass times acceleration, and I know positive forces would be those going forward, and clearly there's sort of nothing there, isn't there? So it'd be 0. Take away then the resisting forces, which is all of this combined here. Okay, equals to mass, which is 0.2 times the acceleration. Okay, now of course we're interested in finding the time, okay, for it to come to rest, and we've got V in here. Okay, so it's actually useful to rewrite A as dvdt. Okay, so we can say that since A equals to dvdt, okay, then I can replace A in here with dvdt, and I've got then like a function of V, so to speak, a function of t. I've got the variables V and t involved, which of course is useful when I want to find the time. So on the left hand side, that just becomes 0 minus, so it just becomes the minus of that bracket, equals to 0.2 dvdt. What I'm going to do then, I'm going to separate the variables. Okay, so I'm going to solve this differential equation essentially. Okay, separating the variables, so I get the v's on one side, t's on the other. So obviously I've got to take that dt up to this side. Okay, I'd leave the minus where it is. Okay, and then I take the dt up, and then of course I take this down and divide, and leave the 0.2 where it is. Okay, with respect to v. So we integrate them both sides. Now a couple of things first. What I would do is that minus I put outside, because it's like -1, so constant, we can take that outside. So I just got 1 in there now. And the other thing I do is, well, I take that 0.2 out on the top there, because it'll be easier to see now how we're going to integrate this. Because 0.2 is a constant, multiplying this fraction of 1 over 0.4 plus 0.6 v dv. Okay, so then we've got this, we need to integrate. This side's really easy, because minus the integral of dt just becomes minus t, because it's 1, isn't it? Integrate, you get t. On this side, you have to be sort of think clever now about how you integrate this, and of course, because it's linear here on the bottom, okay, linear term on the bottom, when you differentiate the top, the bottom, you can sort of get the top, okay, or not quite, but if it's linear on the bottom, you use the ln then to integrate. Okay, when you integrate, you get the ln of the bottom. But when you differentiate the bottom, you have to get the top. So when I differentiate the bottom here, I get 0.6. I haven't quite got 0.6 on the top of now. Okay, so what I do is I place 0.6 there. Okay, so I change this to 0.6. So in other words, I'm timesing the top by 0.6, but to compensate, I'll divide by 0.6 on the outside. So I'm timesing this fraction by 0.6 and integrating it, but to pay back then, I divide the result by 0.6, so it cancels it out. So what I've got then is, well, 0.2 over 0.6 is 1/3. And then, because when you differentiate the bottom, you get the top. I can say ln then of 0.4 plus 0.6v. Okay, I can put round brackets because v is speed, positive, so I know the ln result's going to be positive, or the inside the bracket's going to be positive, so I don't have to worry about putting modulus signs there. Okay, and then don't forget to put your plus c. All right, so then I can use the information I've got. So we know, of course, at the beginning, when t is 0, v is equal to 2. Okay, so substitute that in. So I've got minus 0 there, which is just 0. Okay, equals to 1/3 ln 0.4 plus 0.6 times 2. So replacing v with 2. Plus then my constant. So this implies then that the constant, if you work that out, you get 1/3 ln 1.6. So obviously you've got to take that over to the side to get c on its own. So it'll be minus 1/3 ln 1.6. Okay, so putting it back in here, I get minus t equals to 1/3 ln 0.4 plus 0.6v minus 1/3 ln 1.6. So we'll continue this on the second part of the video.